Hey guys, I'd like to welcome you to our first lecture in organic chemistry. Chapter 1 has a lot of review in it, but we're going to spend some time to kind of dust off those cobwebs a little bit, and then we'll jump into Chapter 2, guys. So let's take a look here at our first little section of organic chemistry, which is structure and bonding of organic molecules. So what I want to look at first with you guys is just the general origins of organic chemistry. So the modern definition of organic chemistry, it's the chemistry of carbon compounds. Carbon tends to form strong bonds to other carbon atoms and to a wide variety of other elements. And this is special to carbon. Not every atom on the periodic table does this. In fact, all living creatures are composed largely of complex organic compounds that contain carbon. Among other things, there's nitrogen and oxygen and hydrogen and some other elements too, but largely carbon. So the other thing that happened is that at some point in time, it was the 19th century, a German chemist took ammonium cyanate, which was an inorganic molecule, and upon applying some heat, created what we call an organic molecule, which is urea. So that was the dawning of kind of organic synthesis. And we're going to see that a lot in organic chemistry, where we take molecules and we transform them into other molecules. So the other thing is that the distinctive feature here of organic compounds is they all contain one or more carbon atoms. So here's a nice little photograph from our Wade textbook, which shows a variety of different chemical compounds down here. So we see vitamin C, something perhaps familiar to us all, and morphine, and a couple other carbon compounds that are somewhat quite complex too, as we look at them. Now that being said, not all carbon compounds are considered to be organic, right? So diamond is just a bunch of carbon atoms, and same with graphite, carbon dioxide. Well, these are molecules that have carbon but are not considered to be organic molecules. So guys, let's take a look here at our first section of this chapter, which is types of chemical bonds. Again, something you've probably seen in general chemistry, but it's worth a little bit of our time to review. So question number 1, why do atoms form bonds? So it turns out that most main group atoms, group 1 and 2, elements 13 through 18, will likely try to have 8 valence electrons to completely fill their valence shell. This is something that we all know as the octet rule, right? 8 electrons. Now there's some exceptions to this. So hydrogen only needs 2 electrons. That's the duet rule. It's what we typically see for hydrogen. Boron and aluminum are stable with only 6 valence electrons. They're called incomplete octets there. And sulfur and some of the other atoms have expanded octets. And sulfur is row 3, and sulfur is going to have d orbitals available for bonding. Now, there's 2 types of bonds that we basically are going to be talking about here. The first one is a nonpolar covalent bond. So if you look at our structure right here, here's a hydrogen and another hydrogen atom kind of connected together. Okay, so it's a sharing of electrons. The other is a polar covalent bond. And then the third is ionic bonds. So let's take a look down below at that in a little bit more detail. Kind of the classic way to talk about ionic bonds, it's a transfer of electrons between atoms. So down here below we have solid sodium, and sodium has a 1 valence electron in the s orbital, and it donates it to a fluorine atom. Now fluorine doesn't just float around as this structure, but this is the classic way to kind of display or show this electron flow. Now the result of that is that sodium has a positive charge and fluorine has a negative charge, so we call it fluoride. So here's sodium fluoride. So this interaction that we see here between these 2 atoms is caused by essentially their opposite charges. So typically the other thing to recognize here is that this type of bond usually forms between metals and nonmetals. So we can, through inspection, we can look at the periodic table and quickly figure out if we expect to see an ionic bond. Now the other type of bond that's present here too is a covalent bond. So this is another strategy, and this strategy involves the sharing of these valence electrons. So the sharing can be equal, like between two hydrogen atoms, or between two diatomic atoms, right? So if they're equal between them, then we say that it's a covalent bond, a pure covalent bond. So sharing of electrons that are equal. It has to do with electronegativity here. And then the other one is called a polar covalent bond. So this is unequal sharing of electrons. So in the example that we see here, here's a hydrogen atom connected to chlorine. Right? You have your lone pairs on here. And chlorine is more electronegative than hydrogen is. So there's actually, and we're going to go over this in a minute, but there's actually a dipole that gets pulled that direction. So this is a polar covalent bond. Now, the type of bond, again, here, as I just mentioned, depends on the electronegativity difference. Now, for me, I don't expect you guys to memorize electronegativities. It's something that you guys can look up. But there's some ones that we just kind of have to commit to memory. So we know that halogens, for example, when we look down here, fluorine, chlorine, bromine, and iodine, those are going to be of high electronegativity. And remember, the trend generally increases as we go up and to the right of the periodic table. So over here you have the highest electronegativity, right? And down on the bottom left would be your lowest electronegativity. So what we can simply do is we can take a look at this table and we can figure out real quickly what type of bond we have. So an H atom and an H atom, because they're both the same atom, the dipole gets pulled equally. It's like a tug of war with two equally matched teams. If we come over here and look at carbon, so we put a carbon atom on here, and then have a some halogen like bromide. So bromide would be a 3. The dipole, as far as its electronegativity, the dipole gets pulled towards the bromine atom. So remember that the arrow always points to the more electronegative atom. So bromine's more electronegative, so we're going to point down to that atom. And what that does for us in the end, and we'll talk more about this, but on that carbon atom there, it actually leaves us with a delta plus charge. And this is interesting in chemistry because atoms that have negative charges are going to kind of want to be close to this delta plus charge. So they kind of attract each other. And of course, if the electronegativity difference is very large, like between a metal and a nonmetal, then we end up with an ionic bond. So there's a couple problems that you'll encounter as you go through your organic life. As far as organic chemistry is, sometimes they'll ask you to calculate these numbers. So if you have to do this on a test or something, the numbers would be given to you from my class. So delta E greater than about 2, we usually say that we have an ionic bond here. And again, typically between metals and nonmetals. If we equal 0, that's a nice pure covalent bond. If it's between 0-ish and 2, then we say it's polar covalent. Now, guys, the other thing that we need to take a look at here is how do we predict if a molecule is polar? Well, to do that, we're going to generally look at two things. We're going to look at the individual bond polarities, okay? And that includes atom size, that matters also, and the geometry. So how do these dipoles, how do they add up? Let's look at an example of something like this. So let's work through this one together. So what if we have something like this? So kind of a classic example here. So this is the Lewis structure for carbon dioxide. Now, when we look at this thing, we can come over here if we have to, All right, carbon's 2.5, oxygen's 3.4. So the dipole should be pointing towards the oxygen atom. So if we had to draw our dipoles in, we would draw them in like this. So this is, again, this is a tug of war with two oxygens that are equally matched. So because of that, the dipole in this mode, or this drawing, the dipole of this cancels out and the dipole is 0. So we'd say that this is basically a molecule that has no polarity to it. All right. Other thing matters here too is we can get into other shapes. So what about, a shape like this? What if we have a carbon and a hydrogen? And we'll get into this a little bit more as we go through the rest of this chapter. But carbon, when it has 4 single bonds to it, has this tetrahedral shape. And you may have remembered drawing this thing out kind of like this, with an H atom kind of going back. So this wedge and dash represents an H atom coming forward. That's what the wedge is. And then the dash represents the H going back. Right, and then we can come up and we can look at our table if we need to. Right, again, we'll kind of get a pattern of this pretty soon. But carbon's 2.5, H is 2.2. So dipoles are getting pulled down to our carbon atom. But it turns out, because we have this equal degree of bonds kind of pointing in this direction, that these things cancel each other out. So this and that end up having a net dipole that points that direction. And then these two guys over here, going in and out of the plane, point the opposite direction. So this molecule has no dipole. Right, the bond dipoles add up to 0 here. But if we took any atom on that and we replaced it with like a halogen, then we would change the situation, right? Because now our dipoles are not adding up the same way. So we point in here, in. But remember, chlorine has a larger dipole than carbon, so we're going to see a dipole that gets pointed up that direction. Right? So this molecule has some level of polarity to it. Now, whether or not the molecule is considered really to be polar, it's really a matter of what you're comparing it to. So we're going to talk about that a little bit more as we go through some lab stuff.